He will speak on complete cohomology of Shimura curves and p-Adic Jacquet-Langlands correspondence.
Great. Thanks very much. Yeah, so like David says, I'm talking about complete cohomology of Shimura curves and Jacquet-Langlands correspondence. I won't write out everything, but so I'll just start out by setting up some notation so I can describe what I'm going to talk about a little more precisely. So first of all, I'm going to fix a prime P, and I'm going to be looking at the arithmetic of a totally real field f over q with degree d. And just for simplicity today, I'll assume d is odd. And I'm going to be comparing the arithmetic of two different quaternion algebras over F. And again, for simplicity, I'm just going to fix for precisely the two quaternion algebras I'm going to look at. So first of all, D over F will be a quaternion algebra which is ramified at d minus 1 infinite places. And it will be split as all the finite places of F. Then my second quaternion algebra d primed, well, at the infinite places it will ramify precisely where d does. And in addition, it will ramify at two finite places, which I'll denote by lambda 1 and lambda 2, and I'll assume they don't divide P. So finite places there. Okay, it's two quaternion algebras over F. And attached to the unit groups of those quaternion algebras, or if you like the restriction of scalars down to Q, are two reductive algebraic groups, G and G primed over Q. I'm going to be interested in automorphic representations of those groups. And I'm going to fix maximal orders inside the quaternion algebras. And an isomorphism between these two algebras at the places away from lambda 1 and lambda 2. Yeah, great. And this isomorphism should be compatible with the choice of maximal orders. So, Jacquet-Langlands functoriality gives us a map from automorphic representations of G primed. So G primed. So certain automorphic representations of G. And this map will identify the local factors of these automorphic representations at the places away from lambda 1 and lambda 2, where we fix these isomorphisms between the quaternion algebras. Great. And I'm going to be interested in pedically interpolating this correspondence, or rather a certain kind of sub-correspondence, if you like, where you just look at the ones showing up in the cohomology of Shimura varieties attached to G and G prime, which in this situation are just Shimura curves. So if we just look at the things showing up in those cohomology spaces, well, then we get yeah.
Can you speak up because it's hard for me to hear?
Yeah, sure. Yeah. Okay, so right, I'm going to look at the orthogonal representations showing up in the cohomology of Shimura curves attached to G and G primed. So where am I? Yeah. So here we'll have cohomological orthogonal representations pi primed of G primed VDLs. And I'm going to look at the ones which are, if you like, unramified at the places lambda 1 and lambda 2. So the local factor at lambda will have invariant factors under the maximal order in D primed at the place lambda units of that. So that would be non-zero. Lambda equals lambda 1 or lambda 2. And those will map into the cohomological automorphic representations pi of G of VDLs such that well, these will have Iwahori level at the places lambda 1 and lambda 2. So pi lambda are fixed vectors under U naught lambda for lambda equals lambda 1 or lambda 2. And if we just restrict to the automorphic representations here which have one-dimensional invariance under these Iwahori level groups, then this will actually be a bijection. And we'll be looking at kind of lambda new things over here. Okay. Right, so yeah, more precisely, this is the correspondence that I'm going to be p-Adically interpolating. And I'm going to do that in kind of two separate but related ways. Firstly, I'm going to so p-Adically interpolate this. Firstly, into a map between systems of Hecker eigenvalues appearing in the completed cohomology of a Shimura curve attached to G primed with appropriate tame level, but I'll make this all precise later in the talk. Right, and over here will be the systems of Hecker eigenvalues appearing in completed cohomology for the Shimura curve attached to D, where the tame level will have kind of the Iwahori level that replaces lambda 1 and lambda 2. Okay, so that's one kind of p-Adic interpolation. And the other kind of interpolation is going to be maybe, if you want, you could call it like a finite slope overconvergent interpolation. And that's actually going to be a map between eigenvarieties showing up in this situation, which I'll explain more about later. But we'll get some embedding of eigenvarieties where these are p-Adic rigid analytic spaces which parameterize, well, they p-Adically interpolate certain ones amongst these classical automorphic representations. In particular, they interpolate the ones which are places dividing P. They're either special or principal series. Okay, and the way I'm going to construct my eigenvarieties and discuss this interpolation is going to be using completed cohomology and Emerton's construction of eigenvarieties using his locally analytic Jacquet functor in that context. Okay. Right. In order to produce this correspondence at the level of completed cohomology, I'm going to use a certain geometric realization of the classical Jacquet-Langlands correspondence, which is kind of p-integral. And that's due to Ribet when f equals q, and Rajaei for f for general territorial field. So, and to do that, I need to talk about integral models for certain Shimura curves attached to the groups G and G primed. So that's what I'll discuss now. Shimura curves and integral models. So I'm going to be interested in certain level subgroups. So they're going to be compact open subgroups of the finite identic points of G or G primed. So I'll call the levels U and V. And attached to a choice of a level subgroup is going to be a Shimura variety. First of all, just defined over C if you like. So I'll call it SHD. UC for the G case. It's just given by quotient of GQ acting on finite identic points of G, product with complex plane minus real line, and quotient by our level subgroup, which is U here. So here the level subgroup acts on the finite identic points of G by right translation. It acts trivially on this symmetric this space, and GQ acts on finite identic points of G by left translation under the diagonal embedding. It acts on C minus R under, well, first of all you embed GQ into GR, and then you project at the unique infinite place where the quaternion algebra D was split. So that gives you a map to GL2R. And then this acts on C minus R in the usual way. Great. And right, one can make the same definition for V and G primed. And then these are compact Riemann surfaces. The theory of Shimura varieties tells us that they have canonical models as projective algebraic curves over F. I guess I'm assuming that D isn't 2 by 2 matrices over Q. So yeah, SHDU over F, SHD primed V over F. Right. So now for a place lambda equals lambda 1 or lambda 2, well, I'll call the ring of integers in the completion F lambda O lambda. And we're going to be interested in integral models of these Shimura curves over O lambda for certain particular level subgroups U and V, or at least level subgroups U and V which have particular type at the factors at the factor lambda. So firstly, suppose a factor of U at lambda just looks like a copy of GL2O lambda. Then, I guess it's due to Morita, also Cariol. The Shimura curve SHDU has good reduction at lambda. So in particular, we get a smooth integral model, which I'll call SDU over O lambda. So smooth proper integral model. Now we consider a slightly smaller level structure. We have U with the factor lambda of this type, and then we consider U intersect U naught lambda. So this is the Ohori level structure, so it's things which are upper triangular when you reduce to the residue field of the place lambda. Then I think it's due to Javis. This is kind of applying the method of Katz-Mazur for modular curves. That we have a good semi-stable integral model, SD U intersect U naught lambda, over O lambda. And the structure of a special fibre of this integral model is that, so the special fibre looks like two copies of the smooth special fibre of this curve intersecting transversely at the supersingular points. Okay. Right, now, the final integral model I'm going to be interested in is going to be for the Shimura curve attached to G primed. So now our level subgroup was V, and so finite zodiac points of G primed. And we're going to assume that this level is ramified, if you like, at the place lambda. So V lambda should be isomorphic to the units in the maximal order of the quaternion algebra at the place lambda. Then I guess it follows from work of Cherednik and also Buteau and Zink give a kind of moduli theoretic description building on work of Rappaport-Zink. But we have a nice lambda-adic uniformization of this curve described in terms of the Drinfeld lambda-adic upper half plane. And the output of that, it's basically you get an integral model S d primed V over O lambda, where the special fibre is a bunch of rational curves intersecting at certain points, and one can describe the structure of that special fibre in terms of, if you like, its dual graph. So the dual graph of the special fibre of this curve. I'm not going to write it down precisely, but it has a nice kind of combinatorial description in terms of a definite quaternion algebra. So it can be described in terms of a definite quaternion algebra, which I'll call D primed, where we've kind of interchanged the invariants at lambda and infinity. So D primed is a quaternion algebra which is ramified at all infinite places. And it's ramified at, it's split at lambda, and it ramifies at the other place where D primed ramified. So it's split at lambda, ramified at lambda bar, if you like. So if lambda were lambda 1, then lambda bar would be lambda 2. Okay. Great. So it's something about integral models. Okay. Yeah, absolutely. Yeah. Is that okay? I can see it.
There's some kind of diffraction there.
Yeah, I probably need that. Sorry about this. Ah, is this precisely for this purpose?
They're always using
Yeah, they're kind of essential to like continuing really. All right, there we go. Right. Excellent. So I can rub out this now, I think. So using the integral model I described for well, this integral model SDU, I'm just going to briefly talk about Mazur's principle. So this section is due to work of Javis. So state a theorem. So suppose you have a continuously irreducible mod p Galois representation rho bar from the absolute Galois group of F, which I'll call GF, GL2 FP bar. It's going to be continuously irreducible. And suppose it's attached to, so it's for residual representation of a Galois representation attached to a Hilbert modular form. Say with level u intersect u naught lambda. If you want, you can assume that Hilbert modular form is lambda nu. And suppose rho bar restricted to a decomposition group at lambda is unramified. So the character 0 representation attached to this Hilbert modular form won't be unramified. It will look like some ramified extension of two characters whose ratio is a cyclotomic character, but it's possible for when you reduce modulo p that extension to become trivial, and then you get something unramified. And yeah, suppose moreover that the norm of the place lambda is not congruent to 1 mod p. So that means that the mod p cyclotomic character evaluated at for lambda, and for bness at lambda, isn't equal to 1. Then the conclusion is that rho bar actually arises, was attached to a Hilbert modular form, level prime to lambda now. So Hilbert modular form of level u. So yeah, I should have said before with the definition of integral models that I'm assuming that my level subgroups u and v are always kind of small enough that all the appropriate moduli spaces will be fine, and so everything works. Later, when I do complete cohomology, I'll be taking limits over all compact open subgroups of that factor at p in those groups, so somehow all my level subgroups will be shrinking. I can shrink them all arbitrarily to make sure that everything works fine. Okay. Great. So a brief sketch of how one might prove this essentially comes from the existence of a certain short exact sequence. So first of all, one looks at the Picard variety of the special fibre of this integral model, ST u intersect u naught lambda. Special fibre of that. That's a semi-abelian variety, and it's an extension of the Picard variety of normalization of this special fibre, which by the description of a special fibre earlier you can write in terms of the Shimura curve with level u prime to lambda. So it's a 1. And here is some toric path of reduction. And if I define, first of all I'm going to fix a coefficient field. So my coefficients are always going to be in either, well, the field E, which is going to be some finite extension of QP, or its ring of integers O, formalised of pi. So I'm going to define a co-character group X check lambda, intersect U naught lambda. It's going to be the co-characters of T, which is some abelian group. I'm going to tensor it up over Z with O. And similarly, X will be the characters of T. If you like, by taking the p-Adic tape modules attached to these objects, one gets a short exact sequence from this co-character group to the cohomology of a special fibre of a Shimura curve at level U intersect U lambda, coefficients in O, to, well, direct sum of two copies of the cohomology of a special fibre of this smooth integral model SDU, where the map here between the two cohomology groups is given by the kind of natural degeneracy mappings down from level U intersect U naught lambda down to level U. And then I guess in order to prove Mazur's principle, the main ingredient is to show that if I take the cohomology of a special fibre and if I localise at some maximal ideal in a Hecke algebra corresponding to the irreducible representation rho bar, that actually gives me something that's isomorphic to the piece of the cohomology of the Shimura curve, the generic fibre of a Shimura curve, piece which is fixed by inertia. So in particular, if our Gauss representation rho bar was unramified at lambda, it's going to sit inside this part of the short exact sequence, assuming our Hilbert modular forms of parallel weight 2. Yes, I'm going to restrict to parallel weight 2 in this talk just for convenience, but one could do everything with non-constant coefficients in the cohomology groups as well. Right, so our residual Gauss representation rho bar will actually sit inside this inertia fixed part, and then by studying the action of Frobenius on this co-character group, one can obtain a proof of Mazur's principle. So I was just sketching that because I'm going to just give some sort of p-Adically completed version of this later. Okay. So now I'm going to talk about the geometric realisation of the Jacquet-Langlands correspondence. So now I'm going to need to talk about the Shimura curve SD primed as well. So I defined X, the character and co-character groups X sub lambda and X check sub lambda. So one can similarly define y sub lambda. Now the level is going to be this v, which is unramified at place lambda, and y check sub lambda. So they're defined analogously to x or x check, but in relation to the Shimura curve st prime, level v over lambda. Great. And now, so I said when I talked about these integral models that the geometry of a special fibre was controlled by a certain definite quaternion algebra, and that's also true for the special fibre of the Shimura curve SD, u intersect u naught lambda. So to be precise, if one looks at so st primes v over special fibre at place lambda 2 now I'm going to talk about. And now if one looks at SD level u intersect u naught, so it's going to be a Hori level at lambda 1 and lambda 2. I'm going to look at the special fibre over place lambda 1. And similarly for SD u intersect u naught lambda 1. And all of these special fibres, the dual graph, if you like, is going to be controlled in some nice combinatorial way by the definite quaternion algebra d primed, which is ramified at all the infinite places, and it's ramified at lambda 1. Yeah, split at lambda 2. Yeah, I don't think I want to say anything more than that. But basically from that description of the dual graph of special fibres, one can deduce a kind of geometric realisation of the Jacquet-Langlands correspondence. So Rajaei is that there's a short exact sequence relating the character group in characteristic lambda 2 of the, so this is for the Shimura curve SD prime with level V. That's going to embed into character group at characteristic lambda 1 for Shimura curve attached to D with level u intersect u naught lambda 1 lambda 2. And the third term will be character group at lambda 1 with level u intersect u naught lambda 1. 2 copies of that. And I mean, similarly to what we had before, the map from here down to here is going to be in terms of 2 degeneracy maps from level u naught lambda 1 lambda 2 down to level u naught lambda 1. And then, I mean, really one should localize everywhere at some maximal ideal in the Hecker algebra corresponding to a suitable, irreducible mod P Garrett representation. And then one can show that the systems of Hecker eigenvalues appearing in Y lambda 2 of V rho bar, well, that's actually going to see all the systems of Hecker eigenvalues which occur in the full cohomology space of the Shimura curve attached to D primed generic fibre of this efficiency in O, localised at rho bar. And this group is going to see all the lambda 1 new systems of Hecker eigenvalues appearing in the cohomology of the Shimura curve attached to D. This will see all the lambda 1 new things occurring at this level. And so if one looks at the kernel of these degeneracy maps, one sees all the lambda 1, lambda 2 new things. So I'll say Hecker eigenvalues occurring in H1 SHD level u intersect u naught lambda 1 lambda 2 localized at rho bar. It's going to be No, this is a mess. Sorry. It's just the lambda 1, lambda nu part of this. Lambda 1, lambda 2 nu part of this. So it's for cohomology classes which are killed under orbital degeneracy maps from level nu naught, lambda 1, lambda 2, down to trivial level at those places. Okay. Great, so this is some geometric realization of a Jacquet-Langlands correspondence, and it's also kind of P integral, if you like. All these things were O modules. So I'm now going to kind of just p-Adically complete that. So I'll first of all talk about completed cohomology of these Shimura curves. So this is a construction due to Emerton.
Are you assuming that the residue degree of lambda is coparameter V?
Yeah.
But have you assumed that to this point?
Yeah, I think so. Oh.
Because the Mazur principle usually works with L equals P as well. Right?
Yeah, but I'd probably have to be more. Yeah, I don't think this works. Well, let's do stuff using monodromy pairings. I mean, maybe one could say something. I don't know. But yeah, I haven't checked it. I mean, I think Mazur's principle for L equals P, one needs to. Is it just the same arguments? Or do you, I'm not sure.
It's morally the same.
Morally, yes. So we'll talk about completed cohomology. So before I had level subgroups, which were compact open subgroups of the finite Adic points of G and G primed. Now I'm just going to be looking at sort of tame levels, so they're just going to be levels at the places away from P. So I'll have U upper P, compact open subgroup of finite Adic points of G away from P, and V upper P, similarly for G primed. And I'm going to define some completed cohomology spaces. So I'll define H1 tilde sub D, tame level UP, coefficients in O, to be an inverse limit over natural numbers S, direct limit over compact open subgroups UP of GQP, of the cohomology of the Shimura curve attached to D with level U upper P times U lower P, let's change to F bar, coefficients in O mod pi to S. Okay, so that's some definition. And this has an action, continuous action of GQP, and it has an action of various Hecker operators. I'm just going to think here about the Hecker operators away from the sort of ramified places in this tame level and away from P as well. And it has a Galois action, the absolute Galois group of F. And the key kind of admissibility property of these spaces is that they're kind of, in Emerton's terminology, they're p-Adically admissible OGQP modules, I guess. So in particular, that means that, maybe I'll put this up here. If one looks at the kind of continuous O-dual of the space, this has some action. Well, for every compact open group G naught of GQP, every compact open group G naught, subgroup G naught of GQP, this has an action of a completed Wasauer algebra attached to G naught, and in this space, this module is finitely generated under this action. Right. And that was a definition for a Shimura curve attached to G. One can, of course, do exactly the same thing for G primed and get H1 tilde D primed, obtain level VP, coefficients in O. And in fact, one can do exactly the same with the character and co-character groups X and Y I talked about before, an X check. And one gets spaces which I'll call X tilde as your characteristic lambda, some level, so it's going to be some level UP intersect unit lambda if you like. And the same for X check tilde and spaces Y tilde, obtain level VP. Okay.
So where you, before you put coefficients in O multiplied to the S, you just tensor the Y with O multiplied to the S? Is that what?
You could do, I mean,
Or you have a different definition?
I think, well, in fact, I define everything in terms of vanishing cycles rather than using the toric part, because that works for general weight. And then one can just, one can do it either way. One can either tensor with O modulo pi to the S, or one can define the things using vanishing cycles with coefficients in O modulo pi to the S, and it will amount to the same thing, I think. There's some issues with torsion, but eventually I'll localize at all these, sort of non-Eisenstein things, maximum ideas in the Hecker algebra, so everything will kind of coincide. Yeah, I can give you some more details later if you like.
I'm sorry, I probably missed the answer, but which cohomology is this?
This cohomology,
Yes.
just a tau cohomology.
For the special fiber?
No, this is the generic fiber. This is the generic fiber. These spaces.
Generic fiber?
Yeah, sorry, that looks like a bold F. So this should just be the global number field F. Yeah. One could also make a definition for the special fiber.
It's actually topological cohomology.
Yeah, but I wanted a Galois action as well. But yeah.
And the other thing on the left, G naught is what, a compact left, right side?
Yeah, G naught is a compact open subgroup,
Yes.
GQP.
And is it obvious, the finite generation?
I mean, this is something Emerson proves, I guess, in his paper on interpolation of systems of economic values. So, yeah, I mean, it's not completely obvious, but yeah, I mean, this is this is almost a definition of this thing being p-Adically admissible. But I mean, yeah, one has to prove it is admissible. Yeah. Okay. So I've defined those things. Great. So now one can essentially p-Adically complete, or just kind of tilderize all the short exact sequences I had before. So the short exact sequence appearing in Mazur's principle, and the short exact sequence appearing in the geometric realization of Jacquet-Langlands Correspondence. So then one can obtain a kind of p-Adic form of Mazur's principle.
Before you do that, can you describe what X tilde lambda looks like, what sort of module it is?
As in sort of what category it lives in. Exactly the same as H1 tilde. So p-Adically admissible OGQP modules. Yeah. So
it has Hecker action but no Galois action.
right. There's Hecker actions and yeah, no. There's a Galois action that says an unramified Galois action at the place lambda.
I mean, is the limit of the finite x's, or is it something worse than that?
No, it's this kind of, you take this direct limit of the finite x's and then p-Adically complete them. P-Adically complete them. So. Okay. Right. So a p-Adic version of Mazur's principle, that's going to be some kind of p-Adic level lowering result. So as a result of Emerson for modular curves, I guess it's due to me in this generality, but the proof's really the same. So if you have irreducible characteristic 0 Galois representation, GF, to GL2 of E, he was our coefficient field, and suppose that rho is attached to or appears in a system of Hecke eigenvalues is attached to a system of Hecke eigenvalues in the completed cohomology space H1 tilde D level U upper P, so U naught lambda. And also suppose that this characteristic 0 representation is unramified at lambda. And I'll also suppose that the residual representation, rho bar, is irreducible, absolutely irreducible. All the assumptions. Yeah. Then rho is actually attached to a system of Hecke eigenvalues appearing in eigenvalues appearing in completed cohomology of Shimura curves attached to D with same level prime to lambda. So again, this is some kind of level lowering result, but I mean the difference is this is in characteristic 0, if you like. The point is that it's possible for a global Galois representation rho showing up in this completed cohomology space to have a local factor at lambda just equal to some unramified twist of trivial plus cyclotomic. And in that situation, this can have, well, congruences with, on the one hand, lots of things which are non-trivial extensions of these two characters. On the other hand, things which are just sums of two characters where the ratio isn't a cyclotomic character. So this is kind of this would be a family of lambda new things, and this would be a family of lambda old things, and the sort of system of Hecke eigenvalues giving rise to this Galois representation is kind of simultaneously lambda old and lambda new. Okay, so that's Mazur's principle. Okay. Sorry?
How do you prove that?
Right, one basically takes the short exact sequence one had it, but I talked about in the proof of Mazur's principle before, and one checks that you can p-Adically complete it and still get a good short exact sequence, and then yeah.
So you do not have the exceptional case that there was in Ribet, right? The condition on the
The condition on the norm of yeah, because we're in characteristic 0, so it doesn't decay. Right.
What is the assumption of residual irreducibility? Is that essential, or?
It's kind of, I think it's maybe essential, I don't know. The residual irreducibility kind of, without that, when you complete things become kind of messy because then you have to consider congruences with things which are not just residually reducible, but reducible in case 0. So somehow it all becomes quite complicated, I think. Yeah, great. I'm going to talk about a p-Adic Jacquet-Langlands correspondence. So before I had a short exact sequence, which I said was a geometric realisation of a Jacquet-Langlands correspondence. That looked like naught goes to y lambda 2 v flies row bar x lambda 1 u, so u naught lambda 1 lambda 2 goes to row bar mapping to x lambda 1 u intersect u naught lambda 1 squared. And again, one checks that one can p-adically complete this situation and get a short exact sequence with tildes on and time levels away from p. I'm going to go to a bigger board now, I think. So, and now one checks that the systems of Hecker eigenvalues appearing in y tilde lambda 2 v localized row bar. One checks that that actually sees all the systems of Hecker eigenvalues showing up in the full completed cohomology space attached to T primed. And similarly, one can check that the Hecker eigenvalues showing up in well, call the kernel of this map x tilde lambda 1 lambda 2 mu. So yeah, that's just the kernel of this map here. So Hecker eigenvalues in that space. Match up with the Hecker eigenvalues in the full cohomology space for D with level UP intersect u naught lambda 1 lambda 2 localized row bar, which are lambda 1 lambda 2 nu in the sense that in the kernel of all the degeneracy maps down to tame level just UP, so where you lose these levels at lambda 1 and lambda 2. Okay, so that's a kind of p-Adic Jacquet-Langlands correspondence in this setting, that the Hecker eigenvalues arising from here match up with the Hecker eigenvalues arising from this space, lambda 1, lambda 2 nu part of this space. Yeah.
Where does the equality go from x to?
Yeah, sorry. In fact, it's equal to the y term. Yeah, yeah. So it's just notation for the kernel of this map somehow. Right. This also has a description in terms of the x side as well. So yeah, great. Okay, so now I can just talk briefly about overconvergent functoriality. So Emerson's construction of eigenvarieties allows one to go from, for example, h1 tilde d primed, obtaining level VP, factorized at rho bar, where one first of all inverts P, so just tensor with E, then look at the locally analytic vectors in here, and apply the locally analytic Jacquet functor. And then one can look at the Hecke operators acting on this locally analytic representation of a torus. So sorry, B is a Borel inside G prime QP. This contains the maximal torus T. This thing is some essentially admissible locally analytic T representation. One can look at the kind of spectrum of the Hecke algebra as acting on this representation space and get a kind of rigid analytic eigenvariety. I guess I'll call it E d primed level VP, factorized at rho bar. This is going to have a map down to T hat, where this is the rigid analytic space parametrizing characters of the torus T, p-Adic characters, p-Adically continuous characters of a torus T. And yeah, one can in this setting one can prove that this eigenvariety is actually equidimensional. And one can do the same for the eigenvariety you get by applying the same construction to all of these spaces occurring in this short exact sequence. And then one uses the, if you like, the fact that the systems of Hecke eigenvalues showing up in the y tilde corresponded to this h1 tilde, and the system of Hecke eigenvalues showing up in the x tilde corresponded to the Hecke eigenvalues in this h1 tilde, to show that you actually get, I guess, an isomorphism between the eigenvariety attained by constructing, by applying Emerson's construction to h1 tilde d primed. That is the same as the eigenvariety you get by applying the same construction to the lambda 1, lambda 2 new part of the completed cohomology for D with level UP intersect u0 lambda 1, lambda 2. So one gets this kind of isomorphism of eigenvarieties. And right, so I'm almost done, but I'll just comment that there are other ways to prove this kind of overconvergent functoriality, producing maps between eigenvarieties. So particularly, in particular, Chenevier did this for the case of a definite quaternion algebra over Q and GL2 over Q, but his machinery works much more generally. It kind of doesn't quite identify the image in the same way as this construction does. Here we see that the image of a Jacquet-Langlands map is really the overconvergent classes coming from lambda 1, lambda 2 new forms, whereas with Chenevier's formulation, you're just kind of, you're doing some kind of p-Adic analysis to interpolate your functoriality. So all you can tell is that your image is the Zariski closure of the classical lambda 1, lambda 2 new points. And it's not clear that that's quite the same thing, but it turns out it is, and one can prove that using these techniques. But there's another cohomological construction of this sort of Jacquet-Langlands functoriality, I believe due to Harris, Jovita, and Stevens, which uses Stevens's cohomological construction of eigenvarieties, but I don't really know anything about that. But yeah, I'll mention that. Okay. Yeah, I'm done.